Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. The Trans-Alaska Pipeline was designed to accommodate large lateral motion across the Denali Fault. In 2002, the pipeline survived a magnitude 7.9 earthquake that created 5.5 meters of lateral displacement under the pipeline. This is a map showing shaking intensity reported by people, basically how strong the shaking was at different places. Shaking was felt from northern Alaska all the way to Seattle, and this map shows these intensity values. Our focus is on the pipeline crossing of the Denali Fault. This figure from Eberhard Phillips' paper shows the earthquake rupture from the Susitna Glacier region, went 340 kilometers to the east and onto the Tachunda Fault. Our focus here is on the crossing of the Trans-Alaska Pipeline. And in that section, it also parallels the Richardson Highway. The first part will look at geological studies done before the pipeline. These are prior to pre-1974, and there are two big ones. The final environmental impact statement volumes that were published in 1972 by a special interagency task force, and then also a report by Clough and others based on investigations performed following that report between 1972 and 74. This is showing the volume of this FEIS report. And although it's somewhat authorless about this special interagency task force, we see that a key chapter says it's prepared by Farians, Kachadurian, Cobb, Page, and these are US Geological Survey scientists. So I would say these are key members of the information in this report regarding the Denali Fault. And in there it says, the southern two-thirds of the proposed pipeline route has experienced large earthquakes, magnitude 7 or greater. An estimate of earthquake risk along the route may be obtained from the seismic history and geology considered in light of large-scale tectonic processes. On this basis, the US Geological Survey, I mentioned some unpublished analysis, divided the proposed route into 5 segments according to seismic risk and assigned to each segment a maximum probable earthquake as follows. And here is a pretty remarkable map. So this is 1972, before the pipeline is built. And these segments are classified segment A from Prudhoe Bay to 67, earthquake magnitude 5.5. Along this next segment through the interior, 7.5. And on this Denali Fault crossing, Denali Dome to Paxson, there's an 8.0 magnitude assigned as possible. 7.0. And then in the south, where in the vicinity of the 1964 earthquake, it's back at 8.5. So this is the map that sets up the expected size earthquakes that the pipeline builders would need to either study more or contemplate the design of the pipeline to account for this. And this is from the appendix, the stipulations report, the earliest I can find of this list. It states, the pipeline shall be designed where technically feasible by appropriate application of modern state-of-the-art seismic design procedures to prevent any oil leakage from the effects, including seismic shaking, ground deformation, and earthquake-induced mass movements of earthquakes distributed along the route as follows. And that shows the same thing that we saw on the map coming in the first volume. What we find in there, it says that prior to applying for a notice to proceed for any construction segment, etc., evaluation of said risks shall be based on geologic, geomorphic, geodetic, seismic, and other appropriate scientific evidence of past or present fault behavior and shall be compatible with the design earthquakes tabulated above and with observed relationships between earthquake magnitude and extent and amount of deformation and fault slip within the fault zone, essentially explaining the kind of information to look for, as well as in that particular fault zone, but maybe also in other parts of the world to get relationships between different quantities. So there it was set up. Key questions facing scientists and engineers in the 70s Where is the fault zone at the pipeline crossing? How much slip can be expected in the largest earthquake here? What is the expected sense of slip? Is it up, down, left, right? What is the maximum expected velocity and acceleration of ground motion? How strong is this going to shake when that earthquake happens? And when was the last earthquake on the fault? Was it in the last decades, hundreds of years ago? The second large team effort was led and shown here in this paper by Lloyd Clough and others. You can see a large number of people involved with this effort to study the details of the fault, from aerial photographs on the ground, and to really a huge undertaking to understand the fault all across Alaska, but in particular the Denali Fault. I really like this picture that appears in their report, trying to convey that a fault is not just a divide between two materials on one side and another material here. It's a broad zone, and they characterize a displacement zone or a fault zone, and then a narrower active fault zone to understand where the deformation might be expected to occur. So fault this size is really a zone that accommodates deformation and slip between these two large blocks. This shows the kinds of measurements that they made for just one section of the Denali Fault, from aerial photographs or on the ground, measurements, locations of the active fault zone, width in the vicinity of the Denali Fault crossing. And here a width of 250 feet was assigned to the active fault zone at the crossing. So they're trying to figure out how wide should we be preparing for and building the pipeline based on the width of this fault zone. What are the design criteria for the pipeline? What criteria need to be met when designing the pipeline? And I'll give two examples. First one, pipeline at location X must withstand an earthquake that produces horizontal displacements of Y and vertical displacements of Z. What are the X, the Y, and the Z for these kinds of statements to be useful? If we look at an example from the environmental impact statement volumes, minimum design criteria for a segment of the pipeline traversing a fault zone that is reasonably interpreted as active shall be: one, that the pipeline resists failure resulting in leakage from 2 feet of horizontal or vertical displacement in the foundation material anywhere within the fault zone, and two, that no storage tank or pump station be located within the fault zone. So define the fault zone and then don't put anything that must have to be there, such as where the pipe has to cross, but don't put critical infrastructure besides that. So where is the fault? Well, as we kind of alluded to earlier, the fault is a wide zone. And this map shows the location of the Denali Fault crossing along the Trans-Alaska Pipeline route. So here is the pipeline, at that time the proposed route in here. This is the Richardson Highway in the Canwell Glacier. This is Lower Miller Creek, Upper Miller Creek. And this shows the author's best interpretation of where this width of the fault zone is. The arrow here tells you which side is going to the right and which side is going to the left. We know that from the large scale geology in Alaska, that the Denali Fault is a right lateral fault system. And this is the Delta River. So for scale, this is showing 2,000 feet scale. And the shaded gray area is the area of the active fault. And this is republished in a couple different papers after the 2002 earthquake, but first appeared in 1974. So the width of the Denali Fault ranges to possibly more than 1 mile where it is concealed beneath present glacial ice. The active fault zone, measured across fault traces and deposits and surfaces of Wisconsin in younger age, is much narrower. The greatest width is measured 580 feet. The average width from 58 measurements is 145 feet. So a huge amount of work that's directly stated from the 1974 study. And a lot of work went into quantifying this width. So a 250-foot width was assigned to this active zone on the pipeline. The design was extended 500 feet on either side to provide a margin of safety for uncertainty in the projection and to account for branch faults splaying from the main fault. The northern boundary was extended 650 feet farther to include an escarpment along a granite outcrop that is a natural limit to the fault zone. Therefore, the active fault crossing along this pipeline is 1,900 feet. Just to break that down with some pictures, there's the inferred 250-foot width for the active fault zone. It's pretty narrow in this picture. Then there's a buffer zone of 500 feet on either side, and then another 650 feet up until this ridge at the north. When we see the design criteria for the pipeline, we'll see numbers 1,900 feet, 250 feet that are listed in the literature, and we can see previously where these numbers come from. So the active fault being that green line in the previous slide, and the full width of 1,900 feet. And you can see at the very end, some endnotes, more information on this table. So one of the key tools that the geologist used was to look at global observations of earthquakes and fault as a guide for what might be expected on the Denali Fault. And this is taken from a USGS report in 1970 looking at earthquake magnitude as a function of the maximum surface displacement offset on the main fault. So look at where earthquakes have occurred globally and where you can get a measurement for both the magnitude and how much lateral offset. You can see the strike slip category here, North America, world. They all show that as you get to larger earthquake magnitudes, you can get up to, in this case, 20 feet or more displacement. And the one on the left is showing the length of the fault rupture compared with the earthquake magnitude. But of major concern is the expectation of how much lateral displacement might be expected on a fault of this size. And so here to show a little more, magnitude 8 in the vicinity of 20 feet, the key statement from the Clough report: maximum credible shift on the Denali Fault estimated by considering the length of the fault, the length of the fault system, and the amount of displacement produced during large historic earthquakes on similar types of fault is 30 feet of right shift component combined with 7 feet of vertical shift component with the north side relatively up. I would point out this explanation, it doesn't explain how they settled on these numbers, but it clearly involved consideration of surface displacements measured after worldwide earthquakes. If one assumes a magnitude 8, like at Wright, then one might expect 20 feet of maximum surface displacement. And as we saw, the FEIS report indicated that this section of the Denali Fault was capable of magnitude 8. And there are other lines, based on the investigators' experience with other large strike slip faults. So there was a new field of study and a lot of experience going into this investigation, a lot of scientific instincts needed to make these recommendations. We'll come back to this at the end, but this kind of breaks up the design criteria, what the pipeline what was expected, what it was recommended to be designed for, and later we'll see what happened. But this breaks the numbers up in this into two categories, one coming from the earlier report published in 1972, and the other coming from the study from 1972 to 1974 looking at the displacements. So what was designed? Here we have a photograph of the custom design in the vicinity of the Alaska pipeline crossing of the Denali Fault. This view is to the south, and we can see these beams that are designed. This zigzagging is standard throughout the pipeline to allow for thermal contraction and minor motion so that it doesn't buckle or strain. That is not the custom part. The custom part is that here it's basically on these beams to allow for a certain amount of sliding. All right, part 2, the earthquake. Here's a picture for the cover of the Fairbanks Daily News Miner after the earthquake, and we can see shake, rattle, and roll. This is from the same building that I'm giving this recorded talk from, Geophysical Institute in Fairbanks, Alaska. Earthquake felt in New Orleans. Pipeline withstands shakedown. Of course, that would be a major question following an earthquake like this, and there it was on the front page. We can see the aftermath of the road torn up at this case, and we can look just to get an idea of where we're examining here. We have the pipeline, the Richardson Highway, and the mapped surface breaks of the fault, where the ground was broken. Extremely detailed map by Peter Heusler and others showing this throughout the entire fault. And here you can see where the crosses the road and the pipeline. And we can superimpose the anticipated fault zone that we saw earlier, shown here with some transparency. And here's this 1900-foot active zone. We can actually see that it actually ruptured the southernmost extent of that zone. So if we bring this in a little more, we can see the right along that southern boundary is where the actual fault break occurred. So based on this comparison, the mapped fault scarps occurred about 152 meters or 500 feet south of the 76 meter or 250 foot wide active fault zone, and on the southernmost edge of the 579 meter wide displacement zone. So now let's look even closer at this crossing. So this is Google imagery from now, but we're looking at the surface breaks as mapped. There's the Richardson Highway, there's the pipeline. You can also find superimpose a figure from a recent paper, after the Denali earthquake by Honegger and others in 2004. We can see here the pipeline, and this aligns very nicely with the figure from their paper and the imagery here. And we can get some idea of exactly the kind of detailed measurements of what happened at the pipeline. So here we'll go a little further. Their figure actually shows where the pipeline was before and after with these dashed and solid lines. It shows how much the pipeline moved on the beams, 2.8 meters, 2.5 meters. And right at the crossing, it's actually not as much as further away where the main fault passed through. And so you can get an idea of how much the pipe actually moved. And you know, given the value of both the pipeline and the material in it and the environment around it, you can see that this is a big deal of whether or not the pipeline would be damaged or lead to any spill, which it did not. And this just shows a photograph of one of those beams just to the south, taken from the front page of the Fairbanks Daily News Miner. You can see that this, which would have been centered on this beam, has shifted and nearly come off. So quite close on some of these cases. A better image of presumably that same beam from Honegger et al. You can see here the beam that this slides on, the foundation, and where the pipeline stood after the earthquake. Here's one of my favorite photos because you kind of see the scale, and most spectacularly, you see that the highway lines are no longer lined up. You can see that the road to the north shifted to the right, and relative to the road to the south. It doesn't take any special training to suspect that the fault went through this area, somewhere in this chewed up patch of the road. And it went under the pipeline. To the left, you can see the pipeline coming into this section where some of the shifting of the pipe occurred and the fault went under. This photo by Peter Heusler. So here's a shot from the road, 2.5 meters of right lateral displacement, meaning that this person is 2.5 meters to the right of where this highway line would have been before the earthquake. So the road in the background moved to the right relative to the road in the foreground. Really spectacular photo. So here's a concept to think about, is that fault displacement is distributed across a wide zone. And even in the 70s, they had an idea about this. The slip doesn't occur just across a tiny interface, but it could be hundreds of meters wide. And so here's a couple published quotations about the type of slip that's occurred. And the main point, and I'll just leave at the bottom, is that about 5.5 meters of horizontal slip occurred across a 200-meter distance perpendicular to the fault. And I'll try to explain this in the next slide. But mainly, you don't see 6 meters at that road crossing. It's distributed. So if you're standing sort of a few hundred meters away, one person would have moved 5.5 meters to the right relative to the person on the other side. And so let's take a look at what's meant by this. Before the earthquake, we have two pieces of material, north of the fault, south of the fault. And we'll be looking at three scenarios of how the displacement could occur. So I'll start with this one. You have two blocks and the fault moves by a distance of d. So there's horizontal displacement d. Everything occurs across the fault. In that case, the displacement is not distributed across a wide zone. It's a very narrow zone of the fault. In the second example, we can imagine that things shift to the right, but there's a wide zone, a fault zone of width w, across which this displacement occurs. So in this extreme case, there's actually no motion right across the middle, but it's sort of like a shearing motion that accommodates the displacement. A more realistic scenario is the combination of those two. So some displacement on the fault, which is what we saw at the road crossing and the main Denali pipeline crossing of about 2.5 meters of slip. And then further away from the fault, there's some additional displacement. So that's the more realistic scenario. And at the pipeline crossing, there's about 5.5 meters of total displacement taken up by 2.5 on the fault, this little notch here, and then another 3 meters spanning out over this 1,000-meter wide zone. So we can look at what this measurements mean, and this is a map showing along the entire fault system, there were detailed measurements made of how much horizontal slip occurred along the fault. So from northwest to southeast, here I'll focus on two examples. This shows the pipeline crossing here. Tap here at the bottom is a pipeline crossing. And there was 5.5 meters of horizontal displacement. The pipeline was designed to accommodate 6.1 meters. So the proximity of this red dot to the blue line shows that things were quite close in terms of the design criteria and what actually happened. If we look at other parts of the fault, say further down to the east, to the southeast, there was actually 8.8 meters of slip. And that would have exceeded the design criteria. So in some sense, looking at this plot, it was fortunate that this bulge happened to occur in a different spot and not at the pipeline crossing. So this is showing this compilation of detailed geological measurements all the way along the fault and thinking about the design criteria of the pipeline in that context. Here's a view to the south, really nice, showing kind of people and a truck for scale. The pipeline is probably bigger than you might think. People standing there, this is a large beams that this pipe is on. This is where the crossing Denali fault rupture crossed, right in this vicinity. We can see that from the Google Earth comparison that we saw earlier. And just to give you an approximate view, here's this pipe hooking to the left and to the right. That's this right here. And we see here in this key segment right here is over in this photo. Remember, this photo is taken right after the earthquake, whereas this is modern Google Earth imagery, but we're going to explore this section of the pipeline a little more here. Here's a photo taken November 10th, 2002, similar scene of the pipeline crossing. Again, fault ruptures right about under here in the background. And here's an alignment with that original photo, really nice comparison. You can see from, decades later that there are some differences in here. The zigzags were always there. It wasn't like these zigzags were caused by the faulting, but we'll see that this feature is probably the most conspicuous difference that occurred in this photograph. So this is showing on that segment north-south compression caused by slip, horizontal slip on the fault. And you can see that that could be cause for alarm uh, given the deformation and in addition to the kind of shaking that this pipeline experienced. This is showing you a picture. In this case, now we're looking north as usual. The pipeline is running down here. This is the highway, and this is really an advanced topic, but I thought it's worth throwing in there that we have the fault coming down in here with the right lateral motion. So the northern blocks going to the right, and this earthquake rupture comes through here. And the idea is that for this type of motion, the principal stress and compression would be in this direction, the magenta arrows, north-south, and extension would be occurring or opening east and west approximately. And what we find is that the section of pipeline that was kinked due to north-south compression is shown right here. So in this case, this north-south compression at a large scale is most likely driven by actually the subduction of the Pacific plate under North America at this large scale. But it's interesting that where you expect roughly north-south compression, that is what happened to the pipe in that area. So here, getting toward the end, the Trans-Alaska Oil Pipeline survives the quake, a triumph of science and engineering. This is the same photo with some annotations from a follow-up USGS fact sheet in 2003. I would probably add a couple things after this. One was just a little bit lucky. We saw that different parts of the pipeline, different parts of the fault exceeded design criteria. There was some fortune to the size of this earthquake relative to the what was made, and also to add really an impressive display of scientific instincts from 1970s earthquake scientists. It was a new field, and you couldn't have a rigorous way to obtain some of the numbers that were proposed, but they had a great notion of what to recommend based on their experiences. So bracing for the unlikely, the pipeline was designed with the expectation to carry oil for 20 to 30 years based on 1970s estimates of reserves on the North Slope. The USGS scientists, officially the Special Interagency Task Force on Oil Development, identified the fault as capable of magnitude 8 earthquakes, and yet there was no evidence of any large earthquake in the instrumental era since 1900. So when was the last earthquake? And here are some quotes. Despite numerous displacements of surfaces post-Pliocene age on the Denali Fault, there's little evidence of displacement within the most recent several hundred years. Or the philosophy underlying the pipeline was for a high-level earthquake with a recurrence interval of 300 to 500 years. So they're looking at, what I'm impressed with is that a relatively short life pipeline was built to accommodate right lateral horizontal displacements of a large magnitude 8 earthquake, the likes of which had never occurred on the fault as far as anyone knew. And that earthquake did happen and the pipeline survived without damage. That is impressive too. Takeaway topics: geological and environmental studies can be valuable for the design of infrastructures. These are the ones done prior to building the pipeline. It's important to make geological measurements and assess damage to infrastructure immediately after an earthquake occurs because geological markers like fault scarps disappear with time. For earthquakes on large faults, the displacement between the two sides is distributed across a wide zone that can be hundreds of meters wide. And finally, in other places along the fault besides the pipeline crossing, the earthquake exceeded the design criteria, such as where 8.8 meters, 29 feet of lateral offset occurred. Thank you for watching, and stick around for supplemental material. So I have this addendum about the design parameters for the Alaska pipeline. This table appears in the introductory article to a bulletin of the Seismological Society of America special issue on this earthquake. It cites Clough et al. 2003 and references cited within. So this table is kind of important. It's showing what was estimated, how the pipeline was designed, and what happened at the Denali fault. So I wanted to make sure I understood where these numbers came from. So this is the Clough 2003 table, and there aren't specifically citations associated with each of these numbers. So I did my best to try to elucidate where they come from. First one is the 8.0 earthquake magnitude. That is listed in these environmental impact statement reports, likely USGS scientists coming up with this. And this shows that map I showed earlier. They also mentioned in their unpublished analysis. So I'm not sure if the analysis underlying the magnitude estimates are published anywhere, but this is at least a map to point to from 1972. The estimated horizontal acceleration and velocity, that came from a USGS report published in 1972. This shows the table of for a magnitude 8.0, the peak acceleration and velocities that are expected. For what happened, a lot of these numbers can be found in the Eberhard Phillips science paper, these ones right here, of the maximum right lateral slip, as well as what happened at the pipeline. And then from the large Clough study from 1974, the maximum slip values where they would have reported them in feet, but here converted to meters, are shown in the red boxes here. This shows the design parameters in that report where we can get the 1900 feet and some other numbers as well as the statement in words about mainly related to the maximum amount of expected slip and what the design would be slightly less than that. We also saw this 250-foot wide statement of where the expected width of the active fault zone would be at the pipeline within that 1900 feet. That's where that number comes from. These other numbers the original references are unknown to me, so I just highlight them from that table. I have not seen this particular source before, but it's listed and cited. I'm not sure where these particular numbers are reported. I'm also not sure where these are, but for the maximum vertical slip, the best published data related to these can be found in Heusler et al. 2004. And that could probably be used to determine the width of the active fault zone based on the surface rupture. So this just shows the figure from Heusler 2004. This is the vertical displacement as measured along the fault. There's mentions of a 2.7 meter measurement of vertical slip, but you can get a sense that in the pipeline vicinity, there's about a meter or so of vertical slip, but that shows all the data taken.